Welcome to springlib.
This question is moderately complicated, so let's take it one step at a time. We need to use the equations that relate the cell potential to the equilibrium constant. We also need to use Hess's law. The hint suggests that we use the KSP expression and the standard reduction potential for silver. So here's the KSP expression for silver iodide. We have silver iodide solid going to silver ion plus iodide anion. And KSP for this is 1.5 times 10 to the negative 16. We also have a reduction potential for silver ion taking on one electron to become silver solid. And this standard reduction potential is 0.80 volts. Now, we can combine these two equations to get the overall equation, but we can't combine K and E. So we need to convert either the K into an E or the E into a K. It's always better when using Hess's law to work with K values or to work with delta G values, not E values. So let's convert our E standard for the second reaction into a K value. The relationship is K is equal to N multiplied by E divided by the constant 0.0592. This gives us a K value of 3.26 times 10 to the 13. Now if we sum these two reactions together, we'll get the overall reaction in question, which is silver iodide, solid, plus an electron, goes to silver metal, plus iodide. We can now determine the equilibrium constant for this reaction. By recognizing we summed these two reactions together to get the overall reaction in question, so we need to multiply our K values. If we multiply our K values, we'll get an equilibrium constant for this half reaction of 4.89 times 10 to the negative 3. But it doesn't want to know the equilibrium constant, it wants to know the standard potential for this half reaction. So we now need to convert our equilibrium constant into a standard reduction potential. It's simply this equation rearranged where E standard is equal to 0.0592 divided by N, there's just one electron, 1 mole of electrons involved, multiplied by the log of our equilibrium constant. This then gives us a reduction potential of negative 0.137 volts.